Okay, this is the third and final video. We left off with the last video somewhere around here. We now understand all about degrees of freedom. And we have this little trick, this little hack, the cover one method, that can help you figure out how many degrees of freedom a table has. So how do we use degrees of freedom? Well, it's like what we would do with z-scores in a hypothesis test. So we can use it to find out how likely it is that what we're seeing was just caused by chance. Or if we have extreme differences that are extreme enough, we can say that they probably weren't caused by chance, that probably the null hypothesis can be rejected, isn't true. So here we have again this example of the multiple choice test and how to compute. We went through and we computed chi-square. We subtract FO minus FE. Here in the first row it gives us 2. Then we square that, it gives us 4. Then we divide 4 by 10, the expected value, and we get 0.4. And we do that across all these rows, and we add that up. That's our chi-square, 4.5. So to think about this in terms of a hypothesis test, we're doing kind of the same thing that we've been doing all along, except that we have to make sure we use the degrees of freedom when we look up our critical chi-square. That's because for a z-score, we assume a normal distribution. So we're working in that distribution. But chi-square is a family of distributions. And the shape of that distribution depends on the degrees of freedom, the number of degrees of freedom. So 4 will be different than 3 and 2 and 1 and so on. So that's why the degrees of freedom matter. And in this case, if you remember, we have 4 degrees of freedom. We need to know at least 4 of these in order to know that, in order for the last one to be determined, for us to know what the other cell will be. So we have 4 degrees of freedom. And if we look this up on the table, right? So our hypothesis test is an alpha level of 0.05. So we roll back to our table here. We're going to look this up. And then we'll see, let me find our table really quickly. We're going to see what critical value we need. And if you remember a critical z-score, we're doing the same thing. Except with a chi-square distribution, because we square the values in order to get our final chi-square number, this is where we get this name chi-square, we always have positive values, so we're always dealing in this end of the distribution. Is it extreme enough over this way? Is it far enough this way? Is it bigger than this critical chi-square? So here we have 4 degrees of freedom, and we roll over until we're under the column that says chi-square 0.05. So this is a chi-square for alpha level 0.05. And that cutoff at 4 degrees of freedom is 9.488. So you can see that this is different if we had a different number of degrees of freedom. But we're looking for 9.488. And so this, our chi-square statistic of 4.5 isn't bigger than that critical value. So we fail to reject the null hypothesis. What we're seeing is not extreme enough. So it may have just been caused by chance. We don't feel confident enough to reject that null hypothesis. So here's a video link, and I'm going to post this within the module. And if you feel like you could use some extra explanation on this or an additional exposure to this kind of idea, you can click into this link and watch this supplemental video, and it may help you out. So we kind of have this summary of these things that I've been talking about. The chi-square test is an inferential statistic. It's kind of like we've been using our z-score, and it helps us understand a relationship between these two variables in our table. We can use it for nominal and ordinal variables. For interval and ratio level variables, we have the 2 mean tests. But we can't compute a mean for nominal variables or even ordinal variables. If you remember back in the first week of the semester, we talked about that. And that's why that comes into play, because now you can see if your variables are nominal or ordinal, you have this option now. to do this chi-squared test. And the chi-squared doesn't have the same assumptions about the shape of the distribution like we have with a z-score. That's because a z-score is this normal distribution, and we need to assume that our data, or ensure that our data, have that shape to be able to apply these z-score rules. For the chi-square, we're going off of degrees of freedom. So that will determine the shape of our distribution, and it makes it so that we can still do these chi-square analyses even if the data are not normally distributed. So what we're really looking for here is what we sometimes call statistical independence. Is there a relationship between these two variables? Does the dependent variable depend on the independent variable? And that's what we're sort of hoping for. But if not, the independent variable is not useful, at least to help us predict anything about the dependent variable or to speak about that relationship. And again, that happens when the categories within that independent variable are identical, reading across within a category of the dependent variable. So that's just a fancy way of saying they don't help us know anything about the categories of the independent variable, don't help us know anything more about the categories of the dependent variable. So we have the steps for hypothesis testing, and the book brings these up, and I sort of bring them up here because it makes sense at this point, because when we say making assumptions, now you understand, do I need to assume that the data are normally distributed or not? If you're using a z-score, you will need to. If you're using chi-square value, you don't have to. But we need to ensure random sampling in both cases. If you choose your own people, you may just be choosing a certain kind of people, and then we can't assume that that's going to reflect the population in any way. We state our null and research hypothesis, or our null and alternative hypothesis, as I like to call it. We set our alpha level, often at 0.05. And now this makes a little more sense. We select our sampling distribution and test statistics. So are we doing a z-score with the normal distribution, or a chi-square with a distribution based on the number of degrees of freedom? We compute that test statistic, either the z-score or the chi-square. We make a decision and interpret the results. And in all cases, if our z-score, t-score, or chi-square are bigger than our critical value, we reject the null. So a lot of things are familiar here, and there's a lot of carryover from what we've been doing, but we calculate chi-square in a different way than we calculate a z-score or a t-score. And again, one of the big benefits of this is that we can use this technique for a nominal or ordinal level variable, and you'll get some practice with that. So here's some examples of the research and null hypothesis. The null hypothesis is really that there's no difference between the different categories of the independent variable. If we look in the different cells of whatever table we have, even if it's a one-way table or a two-way table, are the values, the percentages in one cell different than the percentages in another cell? And each one is that there is a difference. So what we're really testing is whether we have this independent variable and it's pretty much just the same as the category of the dependent variable. So for example, here we have 30.6% of people that smoke, but 37.5% of men smoke compared to 27.1% of women. So that's what we observe. But we start with this assumption that or it's almost like a little game, right? Let's pretend the independent variables don't help us, or the independent variable, I should say, doesn't help us. What would we see? Well, we would see them equal to this 30.6%, because they would just be the same as the percentage of people that smoke. The independent variable of sex, male and female, doesn't add anything. So here we have 30.6. We multiply that by 240, and we get 73.44. So all we're really doing there is this is the total number of women, and we're finding the number that is 30.6%. So we're turning this into 30.6% of women because that's what we would expect if these categories made no difference. It would just be the same as the percentage of people that smoke in general. It wouldn't be changed by sex. So we're just turning this into 30.6. And as it says here, the rest is degrees of freedom. This is a 1 degree of freedom table, so as soon as we have one cell, we can figure the rest out through subtraction. So 110 minus 73.44 gives us 36.72. And 240 minus 73.44 gives us 166.56. And 250 minus 166.56 gives us 83.28. So we can fill the whole table out just in that way, sort of like a Sudoku puzzle or something. But this gives you kind of a bigger picture of what you can do if you have a table with more degrees of freedom. The arrows are charting out how to multiply stuff, but all you really do, again, is turn this number into 30.6% of the total. Turn this number here into 30.6% of the total number of men. So here you'll turn, you'll take 69.4% of 240 to get the 166. You'll take 69.4% of 120 to get 83.28. So you're just making male and female. You're finding the percentage that makes them equal to this category of the dependent variables. So it's as if to say the independent variable is making no difference. And that's what we call expected value. That's sort of our null hypothesis that we want to test. And it makes sense that it's a null hypothesis because it's no difference in the independent variable. So the way we compute chi-square for this is like what we were doing with the one-way table, except that you can see things are kind of spread out and you'd have to go picking through cells to compare the observed value to the equivalent or the corresponding expected value. So 45 minus 36.72, and then you have to find 65 minus 73.44. So what a lot of people like to do is just string out these two charts into one. And here you have men who smoke, women who smoke, men who do not smoke, women who do not. And then you put the observed and expected values for each into the table to kind of keep track of it, because you have to make sure they stay parallel. You have to keep men who smoke with men who smoke, women who smoke with women who smoke. From there, it becomes really straightforward. We go back to these same steps. We do O minus E. We square that. And we divide that by the expected value. And here the expected values are different each time because it's different based on the category. So here we're going to have 68.5 divided by 36.72, giving us 1.87. 71.23 minus 73.44, giving us 0.97. And again, you'll continue this on. 127.24 divided by 86.28, you get 1.47. And you add this up, you'll get your total of 4.74. That is your chi-square. So now you have chi-square, and you just need degrees of freedom. And again, this is a 1 degree of freedom table. So if we think about the assumptions in our hypothesis test, the setup, the null is that there's no difference between these categories. And the alternative is that there is a difference. Our alpha is 0.05. And we have this chi-square of 4.74 from the last slide with 1 degree of freedom. We can look that up on the chi-square table. So if we go back to that, it'll take just a second. We start with the degrees of freedom, which we know are 1. In this case, not 4. So 1, we still have the alpha 0.05. So that intersection happens right here on the top row in this column, and it gives us a critical value of 3.841. So if our chi-square is bigger than that value, then we're going to reject the null. And if it's not, we fail to reject. So our value of 4.74 is bigger than that critical value, and we reject the null. So this gives support to the idea that there is a difference between the proportion of men and women who smoke. So here is a slide of conclusions, and I'm going to post this right in Blackboard for you to review and go over as much as you like. And hopefully this helps, and good luck on the rest of the week's materials.